Today we're going to look at entropy and the second law of thermodynamics. Previously we've looked at enthalpy, which was one type of thermodynamic function. Entropy is actually the second one, and there's a third one we'll look at later, which is called free energy. Okay, so what we're looking at is we're looking at whether something is referred to as thermodynamically favorable. So we need to talk about that for just a second. The idea behind thermodynamics is that we can predict ahead of time whether a chemical reaction is worth investing in, whether it's worth producing that product, or if it's just never going to happen, or if it's going to happen, how much energy will it take to get that reaction to happen, or if it does happen, how much energy can we get out of this? So from an energy standpoint, this is very important because if we're looking at replacing fossil fuels at some point in the future, thermodynamics is going to help us figure out whether those processes are worth doing. So I'll get more into that as we go along. But first of all, what does it mean for something to be thermodynamically favorable? What it means is that a process will happen on its own without us doing anything, okay, other than getting those components together, or maybe getting the reaction kind of started in a way. Examples of that would be like an iron nail will turn to rust. If you think about it, if you put an iron nail outside in the elements, it will spontaneously, on its own, or thermodynamically, favorably rust on its own. The idea is that we just have to put the iron nail into the elements and it will do this process. Now, in the textbook, they use this word spontaneous. The AP test is substituting it with what's known as thermodynamically favorable. They didn't like the word spontaneous because it was misleading to students, and I understand it, but the problem here is that your textbook uses spontaneous. I still use it in my vocabulary. I will try to change to thermodynamically favorable, but when I'm talking about spontaneous, I am talking about things being thermodynamically favorable. What that means is, from a thermodynamics point of view, the rusting of nails, of iron nails, is favorable. Now, if you think about it, if you put a pile of rust out into the backyard, into the elements, into the weather, that rust is never ever going to convert back into a nail. That is not thermodynamically favorable. So certain things seem to have only one direction in which they go, and they don't go back in the other direction. Gases will spontaneously float a container. So if I have a gas, okay, and I put it inside a small container of gas and I open up the lid and I let the gas out, it will spontaneously fill up this room, right? It always does that. It's never going to be have a lid open and all these gas particles go back into the container. That's not going to happen. Heat always spontaneously flows from hot objects to cold objects. So if you put a pot of water on a stove and turn the burner on, the water will always get hotter. You will never have ice cubes form in that pot of water. So as we said, certain things seem to go in one particular direction. They seem to be thermodynamically favorable. So we want to find a way to predict this thermodynamic favorability. Okay, and the first thing we need to do is make sure that we understand what thermodynamics does and what thermodynamics doesn't do, because there's a little confusion here. So first of all, what it doesn't do, okay, does not consider the pathway. Only we look at our initial and final states. So that's what we call a state function, or we talk about state functions. So it doesn't matter how it gets to the particular point that it's at. All we care about is what was it initially, what was it finally. Okay, it gives information. It does not give information on time or speed. Right? That's all kinetics. So just because something is thermodynamically favorable doesn't mean that it's going to happen right away. So you got to keep that in mind, that we're separating out kinetics from thermodynamics. Okay, what does it do for us? It's going to predict whether a process is spontaneous or thermodynamically favorable. Right? It's going to tell us which direction a reaction is going to go. It's also going to give us information on a particular why a particular process occurs. Okay, we'll get to that a little bit later. And it also is going to tell us the direction at which it will occur. Now, hopefully you remember. Hold on, direction. That should remind you and bring up things like equilibrium and K and Q and all that stuff. So we're going to go back and review some of that in this chapter. It's why I like doing thermodynamics at this point. We can go back and review some stuff for equilibrium. All right, so let's take a look at the next thermodynamic function, which is entropy. Now, entropy is designated with a capital S. Okay, this was devised by a number of scientists, most notably Clausius Clapeyron was the person who came up with this idea. No, I'm sorry, Rudolf Clausius. Rudolf Clausius was the German physicist slash chemist who came up with this idea of entropy. Anyway, that's beside the point. Anyway, what he did was he came up with this idea that entropy is something bound in a system. There's another property of a system. When we think about a chemical process happening, enthalpy changes, right? So if we have a chemical reaction, let's just say this box represents the chemical reaction, okay, and it releases heat to the surroundings, right? Heat is lost by the system. Well, the surroundings gains all that heat. Well, we said that the enthalpy of that system went down as a result of that, right? We said the enthalpy of the system went down. Well, there's also another property, because as that heat is lost, that system loses some energy. And as a result of losing energy, what it tends to do is it tends to become a little bit more organized. Those particles, think about it. If you have a gas, those gas particles are moving around because they have kinetic energy. So there's a lot of disorder in that system. Energy you could think of as spread out throughout the entire gaseous state. But if I turn it into a solid and I solidify that substance, well, now those particles are there, but they're inside the solid and they're just vibrating back and forth. Now in the solid phase, it's more organized. There's more order. And that energy that was distributed throughout the entire container is now condensed into a smaller space. So what he was looking at was this idea of energy dispersal. For you guys at this point, you guys can think of it as randomness and disorder. Okay? The idea that there's more disorder in this gas phase than there is in the organized solid phase. And that is enthalpy. So we would have enthalpy initial, and then we would have enthalpy final. Well, we would say that the final enthalpy is actually going to be, we're looking at entropy measuring the amount of energy or the amount of disorder in the system. Our final solid phase would have less entropy than our initial gas phase, right? The gas versus the solid. And this is what we're looking at is this property of entropy. Now, it's very abstract. I get it. I understand that entropy is not something that's easy to understand, but bear with me and we'll kind of make sure we get it over the next couple of days. Now, first of all, entropy is considered an absolute value. What that means is it's just connected to Kelvin temperature. So you know that if you cool this down at a high temperature, with Kelvin being high, right, a lot of temperature, a lot of heat in there, and then the temperature being lower, we can see that this is becoming more organized. And if I keep doing this, if I keep removing the heat from the system, if I keep letting heat come out, eventually I can get to a point where those particles are no longer moving at all, that they're locked in a solid phase or a rigid state where they're no longer even vibrating. That's what we call absolute zero, and that is where the system's entropy would be considered zero, that there is no entropy in the system at all. Now that's an idealized position, but that is generally the idea there. So processes such as chemical reactions and phase changes can result in a change in enthalpy. And that's what I'm looking at over here. We're changing the entropy from initial state to the final state. So my change in entropy for this particular example that I did over here, we would say the change in entropy for the system, right? I'm just looking at my system. I'm not looking at the surroundings. It's very important that we know that we're talking about systems versus surroundings versus the universe, and that's going to come up quite a bit, so be careful with that. Alright, so my entropy went down because I have less entropy afterwards. So this would have a negative change in entropy. And we're going to look at how do we calculate the magnitude of that change. So you first of all should know how to predict the sign notations of these systems. Like what's happening to the systems. Is it becoming more organized or more disorganized? That is definitely something you want to be able to do, and we'll look at in the next couple days. Okay, so if there's an increase in the entropy, we say that the change is positive. If there's a decrease, we're looking at a negative entropy. You should know how to do that for systems, right? With enthalpy changes. If heat is released, we know that the sign notation is negative for enthalpy. If heat is being added to the system, then we know that the change in enthalpy is going to be positive, right? And those would be changes in enthalpy. We are almost always looking at changes in these systems, by the way. So here's some things that tend to make entropy increase. And this would be a good thing to list if you haven't written anything down yet. Entropy is always going to increase if the number of molecules increases during the chemical reaction. So if you have something like a decomposition reaction, let's just say you have something like potassium chlorate, solid, decomposes into potassium chloride and oxygen gas, okay? You go ahead and balance this. You put a 3 here, a 2 here, and a 2 here to balance this. Well, if we look at this, well, I start with a solid, and I produce two things, even if this is a solid here. We're going from one single substance to two. So we would say that the change in entropy for this particular reaction would be positive, because we're getting more disorder in the system, because we're taking one organized thing and breaking it up into two separate things. The other thing too that's really important here to look for is the state of matter. I start as a solid and I convert to a gas. I mean, that definitely is going to make that very, very good change in entropy and positive. Increasing temperature, because we're adding kinetic energy, so the particles are going to vibrate and move more, so they can add more disorder to the system. And entropy also increases when gases are formed from liquids and solids, which is what I mentioned earlier, and when a liquid is formed from a solid, so it's basically the same thing there. And the last one, if you dissolve an ionic compound into ions. And these are just some typical ones. There are many, many other ways to increase the entropy of a system, but these are typically what you would see on the AP test or in a lot of chemistry stuff that we deal with. Okay? Alright, so the second law of thermodynamics can now be defined. Okay, the second law of thermodynamics is looking at whether processes are going to be favorable or not. Okay, so entropy is what we're looking at here. Now be careful with our designation. We are referring to the entropy of the universe. Okay, this is universal entropy. Okay, so what we find with the second law of thermodynamics is all thermodynamically favorable processes have to increase the entropy of the universe. So anything that's happening on its own is always creating more disorder in the universe. Or if you think about it, spreading energy throughout the universe. This is the natural progression of things in nature, to always go from organized, ordered states to disordered states. Okay, we'll talk more about why that is when we get into class. You don't really have to get into the explanations as to why, but we'll get into that a little bit later. So the second law basically says that nature favors processes that move from order to disorder, from low entropy to high entropy. So we're going to keep, that is our driving force behind this, right? So we're going to always come back and refer to this, but to be honest, we don't want to deal with this universal stuff because it's a little confusing. As I said before, stating what type of entropy we're using, universal versus state versus surroundings versus system, can make a big difference. And a lot of people misinterpret the second law of thermodynamics. Okay, they say that life really can't form because of the fact that if you're talking about universal entropy always increasing, meaning you get more disorder, how can you get organized life from disorder? Well, that's because they're not defining it as universal entropy. We can have our system, and I'll show you this in just a little bit, our system can change its entropy because we're going to break up the universal entropy into systems and surroundings. So as long as this overall process is increasing, this can decrease as long as this compensates for it. Okay, and the Earth would be that. The Earth would have a change in entropy that could actually create organized life as long as the surroundings, the rest of the universe, had became more disordered to override that to make the overall change in entropy. So you got to be careful with what we're defining. Are we defining the system, the surroundings, or universal? Okay, we're going to eventually get to just focusing on our systems because these are hard. Universal and surroundings, it's a lot of stuff to keep track of. We're going to really focus in on this change in entropy for the system. So keep that in mind. Most of the entropies you look at in the AP test are going to be system entropies. Okay, so in order to predict whether a process is spontaneous or thermodynamically favorable, we have to focus in on our universal entropy. All right, and even that we're going to change to something a little bit later. But for now, that's the general idea. Alright, I'm sure I'm losing a lot of you because this is a little confusing. I get it. I understand entropy is not the easiest thing to wrap your brain around in the beginning, but kind of bear with me here. Alright, so universal entropy, if it's positive, we would say that it's spontaneous in the direction that it's written in. Okay, negative, we would say it's spontaneous but in the opposite direction. And at zero, we would say that it's at equilibrium. Okay, perfect example of this would be liquid water converting to solid ice, right? Well, we know that this particular reaction has a particular direction, right? So at temperatures that are below 0 degrees Celsius, then we know this reaction is spontaneous, meaning that it's thermodynamically favorable, that this process will, in fact, produce ice at that point, right? So we would say that the reaction is thermodynamically favorable. But if I change the temperature to above 0 degrees Celsius, well, now it's favorable in this process. Oh, look at that, forward and reverse reactions, right? We're shifting in this direction, producing our solids, shifting in this direction, producing our liquid phase, and it all depends on what the temperature is. And I think you get the idea that if I'm at temperature 0, which one's favorable? Well, they're both equally favorable. So we would have both reactions at equilibrium at that point. So we would have the forward would be favored, the reverse would be favored, and here we would be at equilibrium. And that's why equilibrium is going to be used here. And what we're doing is we're defining equilibrium from another point of view, from a thermodynamics point of view. Now, one thing you should also note is that molecules themselves have a certain level of complexity to them. So the more, if you have, obviously if I have something like hydrogen, that's just two atoms, well there's two atoms of hydrogen hooked together, and there's electrons in here, and they're moving around in these atoms. Now what these are, translational, vibrational, rotational, is that these atoms can kind of spin on those bonds. So they can kind of spin around on those bonds, so the atoms are kind of spinning. These bonds aren't static. This isn't like a real bar holding them together. These atoms are constantly coming together and moving away from each other, so they're vibrating back and forth. And it's also moving in 3 dimensions in space, right? I can actually move this molecule around in space, so it can actually kind of move around. That would be your translational energy, okay? So that would be, don't worry too much about these terms. What you really want to know is what's coming up on the next slide. That the more complexity, the more bonds, the more protons, the more electrons. So if I have something like, C2H4, well now I've got more complexity here because I've got 2 carbons and I've got 4 hydrogens on this structure. Now I've got more protons, more electrons, more bonds, more spinning, more rotational, more vibrational, so the energy goes up, so the entropy of this system is higher than the entropy of this system. So the more complexity, the more entropy we have in the system. And here's your key concept right here, is that the greater the molar mass, the higher the entropy. Now remember, this is a little trick, we did this before, to remembering which one has the higher entropy. But you cannot say that the molar mass is higher, therefore it has higher entropy. You have to say that it has more protons, more electrons, more bonds, because of the fact that there's more particles in there. But this is a quick little way to figure out which one has a higher entropy. And of course, if we increase temperature, we're going to increase those translational, vibrational motions and all that. So as we said before, so as we said earlier, we can get to a theoretical point where we can reach that this is equal to 0. Okay. All right. I know this is going a little long, but I only have 2 more slides to cover, and then I'm finished, because this will be our third law of thermodynamics. And the third law is based on this idea that if we keep removing heat from the system, we can get our entropy of the system. This should be really for the system. Is going to go down to 0 when we get to 0 Kelvin. Okay, so what we would do is we'd remove all of those energy from the system, so our entropy of the system would be at 0. So we can actually have a 0 point on our scale. So this is not like before we said we have to have a change in enthalpy. We can't measure enthalpy. Entropy we can measure. So we can actually get a value for energy. Then I'll talk about that when we look at it a little bit later. But here's the unit though. This is one thing students often miss, is that the entropy, since it's based on temperature, we're going to have temperature in our unit. So we're going to have Kelvin in here. So joule, mole, and Kelvin is a typical unit for entropy. And of course we're going to put in its standard state because of the fact that temperature has an effect. We want to make sure that we're at the same temperature. So when you see that degree symbol, we mean temperature is equal to 25 Celsius and our pressure is 1 atm, and our solution concentration, by the way, will be 1 molar. Okay. All right, let's take a look at one last slide and we'll finish. And this would be your properties of entropy. And it's kind of redundant from what we saw earlier, but when we look at the scales, when we look at, it's almost never, well, it's never 0, but because you really can't get to absolute 0, but there are some conditions where it does and actually goes negative because of our reference points. We're not going to get into that too much. But again, gas states have a higher value than solid states. Generally increases with increasing molar mass. It increases with the number of atoms in the formula, and liquids and solutions have a higher value than the solids. Alright, so hopefully that gives you at least a beginning starting point with entropy, and I will do my best to explain more of this in class. So that pretty much ends it. So thanks for paying attention, and I will see you guys in class.